Hello everyone, welcome to another calculus lesson. Today you will be learning about maximum and minimum. Together we call these extrema. Our learning objectives are: we will define absolute extrema, define local extrema, explain how to find the critical points of a function over a closed interval, and describe how to use critical points to locate absolute extrema over a closed interval. First of all, let's do a bit of exploration. Consider the following functions and identify any maximum or minimum values. Try to sketch a graph of the function. A. Y is equal to x cubed. B. Y is equal to negative x squared. And C. Y is equal to x to the fourth plus 1. Let us sketch the graph of y is equal to x squared. If you don't remember exactly what the graph looks like, you may make up a table of values. And then, by plotting these points on the graph, you will have a curve that looks just like this. Notice here that the graph keeps on increasing all the way up to positive infinity. It keeps on going down all the way up to negative infinity. You may want to think of the maximum as positive infinity and the minimum as negative infinity, but in general, we tend to write no max and no min because we do not have a specific y maximum value or a specific minimum value for the function. It's infinite, so we write no max or no min. For the second problem, part B, y is equal to negative x squared. Again, you can make a table of values and sketch the graph. When you sketch the graph, it will look like some downward sloping parabola with a maximum point at 0, 0. In this case, we write max is at y equals 0 when x equals 0. Here we have no minimum or there's no absolute minimum on this function. Thirdly, y is equal to x to the fourth plus 1. We know then that it's an even function, and it will likely look like a graph of what x squared would look like, but it is a little bit flatter at the base. We could make a table of values if we do not remember exactly what the graph of this function looks like, and then plot those points. Here, when we look at the graph, we see that there is an absolute minimum. That minimum is at y equals 1 when x equals 0. There's no absolute maximum because there's no specific largest y value on it. It all goes out to infinity. Definitions. Let f of x be a function defined over an interval I, and let c is an element of I. That means c, the x value, is included in that interval. We say that f has an absolute maximum on I at c if f of c is greater than or equal to f of x for all x is an element of I. We say that f has an absolute minimum on I at c if f of c is less than or equal to f of x for all x is an element of I. If f has an absolute maximum on I at c or an absolute minimum on I at c, we say that f has an absolute extremum on I at c, where extremum is a combination of or includes maximum and minimum. Note, f of x is the maximum or minimum value. The y value is the maximum or the minimum value. However, we also identify the x values where the maximum or minimum occurs. We generally write x is equal to b where x equals c, or we can write at x equals c, or we can say y is equal to b at x equals c. And here c and b are real numbers. Let's practice some of these. Find the extremum or any extremum of f of x equals x squared on the interval negative infinity to positive infinity. Try sketching the graph. Also try to find an extremum of f of x at 1 over x squared plus 1 on the interval negative infinity to positive infinity. Could do this by try sketching the graph again. Also find an extremum of f of x equals cosine of x on the interval negative infinity to positive infinity. This we could do also by plotting the graph first. Take a look at number 1, where we had y is equal to x squared plus 1. If we sketch that graph, it would look like an upward curved parabola with a minimum at 0, 1. Therefore, we say that the minimum is y equals 1 when x equals 0. There's no absolute maximum. For number 2, for part 2, number 2, if y is equal to 1 over x squared plus 1, notice what the curve looks like. It has a maximum here at 0, 1, it flattens out, going towards 0 at both ends. So the absolute maximum then is y is equal to 1 when x equals 0. And there is no absolute minimum. There's no y value that's the absolute minimum there. Thirdly, let's look at y is equal to cosine of x. This is what the graph of y equals cosine of x looks like. The period here is 2 pi. It has a maximum at 0, and at 2 pi and at negative 2 pi has minimums where x is equal to negative pi and pi. The maximum y value is 1. The minimum y value is negative 1. So we write, for the absolute maximum, y is equal to 1 at x equals 0, and then plus or minus 2 pi, comma, plus or minus 4 pi, dot, dot, dot. That means it continues. The absolute minimum occurs y equals negative 1 at x equals plus or minus pi, plus or minus 3 pi, and this pattern continues. And this leads us into talking about a particular theorem called the extreme value theorem. Well, this theorem says that if f is a continuous function over a closed bounded interval, a, b, brackets, that means a and b are included, the endpoints are included, then there is a point in AB at which f has an absolute maximum over AB, and there's a point in AB at which f has an absolute minimum over AB. So it will have both a maximum, absolute maximum, and an absolute minimum. The function will have an absolute maximum and an absolute minimum over a closed interval AB. Let's just look at some examples. Find any extrema on f of x is equal to x minus 2 all squared on the interval 1, 4 included. The graph is provided. That means that we can look at the graph and we can see a maximum absolute value, absolute maximum value, and a minimum, an absolute minimum. Okay, so we got to determine how we're going to write this. Also for number 5, find the extreme of f of x is equal to x over 2 minus x on the interval 0, 2. We'll also look at number 6, find the extrema of this piecewise function. Okay, for number 4, this graph, we can say then that the absolute maximum, y is equal to 4 when x equals 4. And the absolute minimum, y equals 0 when x equals 2. For number 5, we look for the absolute maximum. We see that there is no absolute maximum because there is no specific maximum y value. It keeps going on and on. But for the absolute minimum, we have y equals 0 when x equals 0. The next problem, we can see that there is an absolute maximum at y equals 2 when x equals 0. However, the minimum on that function is an open circle. Most minimum value for the y is an open circle, so we say there's no absolute minimum. Okay, let's look at some more theory. Local extrema. A function f has a local minimum at c if there exists an open interval I containing c such that I is contained in the domain of f and f of c is greater than or equal to f of x for all x is an element of I. That means your x value will be in this interval, and if you have a x value that is function value is higher than the rest of the other function values, then that's a maximum, local maximum. That means you have values to the left and right of that x value. Similarly, or in a similar manner, function has a local minimum at C if there exists an open interval I containing C such that I is contained in the domain of f, and f of C is less than or equal to f of x for all x an element of I. Now let's look at some problems. Before that, let's look at another bit of information. A function has a local extremum at C if f has a maximum at C, a local maximum at C, and or it has a local minimum at C. And the critical points, let C be an interior point in the domain of f. We say that C is a critical point of f if f prime of C is equal to 0, or f prime of C is undefined. So that is if your first derivative is equal to 0. On a graph, that would look like a maximum or minimum, where your tangent line will be horizontal. So in these two places, f prime of C is equal to 0, the maximum and the minimum. But where there is a sharp turn in your graph, your f prime of C is undefined. Okay, then there's Fermat's theorem. F has a local extrema at C, f, and f is differentiable at C, then f prime of C is equal to 0. That sort of summarizes pretty much what we've been saying, that we have a derivative is equal to 0, then there's a local extrema, a local maximum or minimum at that point. Also, the function got to be differentiable, so we're excluding functions that are not differentiable, such as absolute value functions. Let's look at a couple of examples. Find the critical points of the following function. F of x is equal to 1/3 x cubed minus 5 over 2x squared plus 4x. So first of all, we need to find the derivative. Find f prime of x. In this case, f prime of x will be x squared minus 5x plus 4 using the power rule. We set f prime of x equal to 0, setting the derivative equal to 0, x squared minus 5x plus 4 equals 0. Then that means we could factor it out, or you could use a quadratic formula if you wanted to, and you will get x minus 4, x minus 1 equals 0. So x equals 4 and x equals 1 are our critical values for that function. Problem, f of x is equal to 4x over 1 plus x squared. We want to find the critical values for that function. For this function, then, we find the derivative first of all. Because it's a quotient, we use the quotient rule. Low d high minus high d low over low squared. And so it's going to be 1 plus x squared times the derivative of 4x minus 4x times the derivative of 1 plus x squared all over 1 plus x squared all squared. So we do 1 plus x squared times 4 minus 4x times 2x over 1 plus x squared all squared. So 4 plus 4x squared minus 8x squared all over 1 plus x squared squared. We're doing a bit of algebra right here to simplify it. So finally we have 4 minus 4x squared all over 1 plus x squared squared. That is your derivative. Then we set our derivative equal to 0 and solve for x. So f prime of x equals 0. 4 minus 4x squared is equal to 0. That means the numerator itself will be equal to 0 when we do some algebra. Then factoring out, we have 4 times 1 minus x squared is equal to 0. So x eventually be plus or minus 1. So our critical points then will be at x equals -1 and x equals +1.